So we move on to the topic of optics, and optics is the study of the behavior of light. So we're going to spend a couple lectures talking about the behavior of light. And so the first thing, we're going to be using what's called the ray model of light. And so in this case, light travels through a transparent material in straight lines called light rays. Sometimes I'll draw them like little curvy things here, but either way they'll be moving in straight lines. And one thing is that light rays do not interact with each other, and they can cross each other without being affected in any way. And so the first thing we'll talk about is the speed of light. So light travels at 3 times 10 to the 8th meters per second when it's in a vacuum. Now we'll deal with light traveling in non-vacuums, and we'll use this equation here to deal with that. And so the velocity of light in some medium, like say glass or air, is equal to c, the velocity of light in vacuum, divided by what's called the index of refraction. And we'll use this quite a bit for different kinds of materials. The velocity will be less than c, and so this implies that n is greater, and it's equal to 1, again 1 being in the case of a vacuum. And so here's a table. You got a lot of these tables in the book, or I'm sorry, you'll have a copy of a table like this in the book. So again, in a vacuum, that equals to 1 exactly. So this is the value of n. So some popular ones would be water we'll use a lot, glass we'll use a lot. Again, this is not the kind of thing you need to memorize, but you might be asked to look at this table with homework problems and things occasionally. When light hits an object, 3 different things can happen in general. So the first thing that can happen is it can be absorbed. The second thing, it can reflect, so it can bounce off. And the third thing, it can refract, okay, which means that it goes through and bends as it travels through the material. We're going to deal with reflecting and refracting today. But in general, when light hits something, it does all 3 of these things. We're going to do a lot of little pictures called ray diagrams, and we'll do this for, again, the next couple of lectures. And so rays will originate from every point on an object and travel outward in all directions in general. Okay, this comes from light bouncing off of the material. Now when we're trying to simplify the picture to kind of understand it, we'll use a ray diagram and we'll show only a few tiny rays. And so as just some kind of example, here's the basic idea of reflection that we're going to use, which says that the angle of incidence equals the angle of reflection. And so we usually call theta I and theta F for this. And so the angle is between the light beam and the normal. And this will be our sort of definition. So this is the normal. Again, normal means it's 90 degrees to our surface. So here we're using a flat mirror. And again, that normal is 90 degrees to the surface. And so those angles are measured from that normal. So when we see stuff, what's actually happening, and so here we have a light source, which here is a light bulb, but it could be the sun. The light source bounces its light off of some material. So here my object is like a statue. And so if a bunch of rays will bounce off this tip of the statue and bounce into my eye. And that's how we in general see something. Color is because some of the light is absorbed by the object. So the object absorbs lights of different colors, and we see the rest, and that's how the color of something is determined according to how we see it. Now with reflecting, it works the exact same way, except now the light is bouncing off of some object like a mirror. And so here if I draw 3 rays bouncing off the mirror, we're going to spend a lot of time doing is trying to figure out where the image of this particular object is. And the way we do that is we take the rays that go to our eyes and backtrack them. So in this case, unlike last one, the light is reflecting off of a mirror, so it's not actually reflecting off of the object, but what it appears to be, our eyes, if you look into your mirror, you'll see this object, the light bulb, sort of deep inside behind the mirror. We can formalize this a bit by drawing a couple different rays. So I'm going to draw rays only through the tip of my statue. And so the first one I draw is coming right in and reflecting right back out through that tip of that statue. The next one, I'll draw a second ray at some angle. So angle incidence equals angle of reflection. And what I do is I backtrack the 2 beams. And the ones I want to backtrack are the ones that are hitting my eye. So I imagine that this beam is hitting my eye, and then this beam is hitting my eye. If I backtrack those, then where they meet is the tip of the statue, or the tip of the statue's image. And if you do this with a nice ruler and be real careful, you'll find that the distance behind is exactly d, the distance that it was in front of the mirror. So this is always the way it works for a flat mirror. And this image is something that we're going to talk about before. This is what we call a virtual image. So it's a virtual image since the light rays don't really meet there. They just appear to meet there. And so it's a virtual light ray. And any other sort of beam that I draw or ray coming from that tip, if I bounce it off the mirror and then backtrack that beam again, it should come through that tip. So all rays originating from the peak of our statue appear to converge at the same point behind the mirror. And so our summary of this is the image for this flat mirror appears upright, the same size, it's located the same distance from but behind the mirror, and it's a virtual image. And so we'll talk much more about mirrors as we go on, but this is just our first introduction to one. And just this idea again, we'll hit this again, but a virtual image is an image where the light rays do not actually emanate from the image point. And a real image, which we haven't seen one yet, but we will later, is an image where the light rays do actually emanate from the image point. That was a little bit about reflection, and now we'll move on to refraction. For refraction, it's a little more complicated, and we have an equation that's called Snell's law that explains how this works. And so when light travels from one medium to another, the speed changes that we talked about. The frequency, however, will remain constant, and so in order for this to happen, the light will bend. And so here's the equation that describes this bending. And so it's n1 sine theta 1. n1 in this case is the first material that the light is traveling through, and N2 is the second material. Now one thing that can be tricky is that oftentimes the book will have these switched over, and so it's really important that when you do this you sort of make sure you set up what you want to be N1 and what you want to be N2. And those thetas, the other thing that they can do is the theta is relative to, again, that normal. So here's the normal, which again is 90 degrees to the interface, and so that angle is relative to that normal. You got to be real careful. Books and things love to switch up that angle. Now here's an example of Snell's law. A ray of light traveling through the air is incident on water, and so the two n values are given. Part of the beam is reflected. So like we said, in general, part of the beam will always be reflected, and then part is refracted. And they want to know what is the refracted angle, theta 2. And so again, we know that theta 1 equals theta r equals 60. Now for the Snell's law, to figure out what theta 2 is, here's how we set it up. So again, it's n1 sine theta 1, and so n1 is equal to 1. So we just plug in 1 over there. Sine of theta 1, so that's the initial angle, which was told to us to be 60. And that equals the second index of refraction, 1.33 times sine of theta 2, which theta 2 is what we're looking for. And so if I go through and do this, I get 40.6 degrees. And so let's try an example here. It's more conceptual. Which statement is true regarding the index of refractions for these two mediums? All right. So hopefully you had a chance to do this. I get the answer to be A. And so we take our Snell's law here. So this again, N1 is the first material, N2 is the second material. And if you look here, theta 2 is bigger than theta 1. You can get that just from the picture. Now what that implies is that sine of theta 2 is bigger than sine of theta 1. Right? Because sine of 0, if you just think about it, sine of 0 is 0. And sine of 90, which is the biggest angle we can have in a case like this, is 1. And so as the angle gets bigger, it goes from 0 to 1. And so if the angle is bigger, sine of theta is bigger. And so if that's true, then n1 has to be greater than n2. Right? So in order for these two things to be equal, if the sine of theta 1 is less than sine of theta 2, then n1 has to be bigger than n2 in order for those two things to be equal. Now, one consequence of Snell's law is what's called total internal reflection. And so we use Snell's law for that. And this is the case when you're moving from an index, so here again we'll call it N1, and going to an index N2. But in this case, if you're going from a bigger index, okay, so just for whatever it might be, the N1 is bigger than N2. When this happens, all right, theta 2 is going to be bigger than theta 1, right? So that's basically the way it works. The material with the bigger index of refraction will have the smaller angle. So if N1 is bigger, theta 1 will be smaller. Now you can imagine that there's some angle, we call this the critical angle, all right, where the angle in theta 2 is 90 degrees. And so this is a little bit hard to visualize. So here's my theta 2. Well, in this case, the angle is this whole thing. It's 90 degrees. And so the light doesn't really pass through into the second material. And so it's totally internally reflected, is how we call that. All right, and so this is the critical angle where this happens. And basically, if I was to sort of prove this, I would say N1 sine of theta 1 equals N2 sine of theta 2. And what I'm finding is when theta 2 is equal to 90. And so sine of theta 2 equals to 90 means sine will be equal to 1. And so it equals to N2. And so it's N1 sine, and we usually call this, again, the critical angle. And so this says that N1 times sine of the critical angle equals N2. And so if I just go through and solve for this, what this says to me is that sine of theta critical equals N2 over N1. And here's the actual equation you'll see in the book. It just solves for that theta critical as being the inverse sine of N2 divided by N1. Just got to be careful. Again, this only happens when N1 is bigger than N2. If N2 is bigger, you can't have sine of something bigger than 1, right? So that's sort of the limiting part of that. And then just to kind of reiterate, what this means is if a light beam comes in at a larger angle to the critical angle, like over here, it's going to come in and be, again, totally internally reflected. And so if it comes in at greater than that angle, it's not going to be able to leave the material. Let's try an example here. So here's a question, old test question. A laser beam travels from an area of unknown material into an area of water. So the first index N2 is unknown and N1 is 1.3. What is the minimal refractive index of the unknown material such that a ray hitting the interface at an angle of 48 degrees to the normal will be totally reflected? Give this one a try and we'll talk about it. All right, hopefully you got choice C. That's what I got. And so let's set this up. Now you got to be careful sometimes with these book type problems. So we have this nice equation for total internal reflection. Now the problem here is that they switch up which one's N1 and N2 on you. So I usually just start fresh every time. It's maybe not the fastest, most efficient way, but for me it works out well. So N1 is 1.3, and the sine of theta in this material, so we're trying to find this, to find the critical one, is when this comes off at 90. Okay, so again, the angle from here is 90 degrees. So sine of theta 1 is 90, so that just equals 1. And that equals N2, which is what I'm solving for, times sine, and they say that that angle is 48. And so here I just want to solve for N2, and so I get 1.3 divided by sine of 48, and when I punch that in, I got 1.75. One important consequence of total internal reflection, one use of this is a fiber optic cable. So fiber optic cables are very important in communications and technology these days. And what it is it's literally just a tube of glass. And you shoot a laser beam down it, and basically the laser beam can never get an angle smaller than the critical angle for that particular material. And so what it does is it's totally internally reflected as it travels down this beam of glass. And so you're able to send these communications, these signals, in a very lossless way, and they can travel very far. So it's a nice use of total internal reflection. And finally, we're going to talk about the topic of dispersion. And this is just the idea that the different colors of light have slightly different indexes of refraction. Not enough that you would really notice it in most cases, but in a case, say, of like a prism here, okay, where the two beams are separated, you can definitely see that they have a different index of refractions. They bend in different ways. And one really cool example of both internal reflection and dispersion would be a rainbow. And so a rainbow works when light rays come in. So this is white light from, say, the sun, comes in at some incident angle. And what happens is it comes into a droplet of water in the air. And just like a prism, this water droplet will disperse the light. So they'll get bent slightly differently depending on exactly how they enter into the light, they'll oftentimes have this idea of internal reflection. So they bounce off the back end of the water droplet, and when they bounce out, they come off at different directions. So here this skier sees the red reflection from this particular drop, and then this second drop here, the skier sees the blue reflection. And so the skier will see red at the top of the rainbow and blue at the bottom. And you can sort of draw this out into more detail. So here's actually 3 different drops. So again, the top one gives the red light, the bottom one gives the blue light, and so we just picked green here for the in-between one. But again, so rainbows are a combination of effect of internal reflection and this idea of dispersion.